Hi, and welcome to my presentation on machine learning for monitoring, review, and testing at financial institutions. Let me start by sharing an anecdote which in hindsight exemplifies the challenge financial institutions face when implementing machine learning and big data analytics. Few financial institutions have cracked the code on effectively deploying machine learning for automating business-critical processes. Whilst the pace of adoption of machine learning algorithms accelerated during and after the coronavirus pandemic, implementing machine learning-driven applications remain a challenge, particularly for banks. 5 years ago, our then global head of risk and compliance embarked on an ambitious digitalization initiative, with the aim towards a data-driven and analytically enabled risk and compliance function. The initiative included the exploration of potential applications of big data analytics, robotics process automation, and machine learning. We were like explorers who ventured into the unfamiliar landscape of these new technologies, and were spurred to identify areas of our work that could be optimized, improved, or automated. There have been successes such as the rollout of simple script-based bots for automating mundane or repetitive steps in a workflow, and other tools that aggregate information for easy access. Also, there were missed opportunities, and I recall one notable presentation by our data science team that demonstrated an all bells and whistle trade surveillance platform underpinned by machine learning algorithms. Despite the impressive dashboard of graphs, heat maps, and charts, the team was unable to get buy-in from the business or from control functions for one reason or another. These examples show that the adoption of big data analytics tools, rollout of robotics process automation initiatives, and exploration of machine learning use cases in financial services has been a long and winding one. It is an exploration beset with false starts and dead ends. Machine learning's potential use cases in risk and compliance have been both promising and confusing, and at times overhyped or unexplored. In this paper, I propose a novel use case for machine learning in risk and compliance management, which has the potential to drive greater performance across many compliance processes, which are highly manual or supported by outdated tools. Particularly, my research identified a gap in available literature that explores, evaluates, or demonstrates the application of machine learning for monitoring, review, and testing performed by internal control functions at financial institutions. My research bridged the gap in theory and practice by evaluating, assessing, and demonstrating the viability of automating controls testing for Volcker Rule compliance that seemed unwieldy or impractical under conventional programming. In this research, we take on what looks to be almost impossible and propose a novel use case that could unlock the value of machine learning in optimizing risk and compliance processes. The proposal in this research is not just automating for automating's sake. My research offers a minimum viable product and proof of concept that solves a real-world business problem. I created the Financial Services Machine Learning Use Case Deployment Atlas to visualize and illustrate the truly novel contribution of my research in risk management. Let's now take a moment to talk about the atlas in detail. The unique feature of the Machine Learning Use Case Deployment Atlas is organizing the seemingly disparate use of machine learning at financial institutions under a widely adopted risk management framework, which is the 3 lines of defense model. In this framework, business front office functions are the first line of defense, risk management and compliance functions are the second line of defense, and internal audit is the third line of defense. Most of the available literature explore the deployment of machine learning in risk management for anti-fraud, anti-money laundering, combating the financing of terrorism, credit risk modeling, and transaction and communication surveillance. In particular, academic and industry papers appear to focus on credit risk management, specifically credit scoring. Nevertheless, there are studies that cover market, liquidity, and operational risk. The Atlas is a navigation tool for risk managers and compliance professionals to facilitate understanding of machine learning use cases in their respective discipline and possibly drive adoption and ignite the exploration of machine learning for financial and non-financial risk-related applications. The atlas clearly illustrates in which domains my research demonstrated a truly novel way of deploying machine learning for compliance management. The atlas shows the contribution of my paper under the broader umbrella of non-financial risk. Likewise, the atlas displays potential intersection of machine learning use cases across the three lines of defense functions, including financial risk management and internal audit, substantive, and controls testing procedures. My research is novel in that it frames the controls testing robotics process automation challenge as a classification and prediction problem, which a variety of machine learning algorithms can solve. Let me now show you how I implemented my work, specifically the methodologies for generating synthetic data, feature engineering, and implementing machine learning algorithms such as logistic regression, linear discriminant analysis, and neural networks-based models. Due to confidentiality and UK regulatory data handling restrictions, my research is constrained from utilizing genuine lending and fixed income securities related transactions in training and testing machine learning models. As an alternative to using genuine financial transactions, I sought permission from one of the leading investment banks based in London to use instead the data features which defines a vector of data constituting a typical matrix of financial transactions. The first step involves generating synthetic data for my research by extracting data attributes from actual lending and fixed income transactions without reference to client-level information recorded in an investment bank's trade capture systems. I then wrote code within the R programming environment that generates synthetic data for 3 Volcker exemptions, including the non-trading account or NTAC, trading outside the US or TOTUS exemptions, and positions excluded or pose exclusion. I also validated the synthetic data by conducting a fidelity test, which involves senior compliance officers who are Volcker domain experts at the London-based investment bank. The second step involves data wrangling and deploying feature selection techniques such as random forest, best subsets regression, and domain expert judgment. These data cleaning and pre-processing steps are critical, not only for developing efficient models but also for ensuring model interpretability by excluding predictors that are unconnected to the response variable in regression models or target variable for classification algorithms. Given the inherent class imbalance in real financial transactions, I also implemented synthetic minority oversampling technique or SMOTE for error mitigation and to optimize the precision of machine learning models. I then trained logistic regression, linear discriminant analysis, and feed-forward neural networks on separate pre- and post-SMOTE and partitioned and unpartitioned datasets for TOTUS, NTAC, and POST. Subsequently, I evaluate the results based on SME judgment and various statistical metrics such as precision, recall, and F1 score. My research also published the confusion matrix for all empirical tests performed for each of the 3 Volcker exemptions. The last step involves comparing the results from the machine learning models, assessing the outcomes based on SME and domain expert judgment, and recommending areas of further research. My research not only developed realistic simulated financial transactions, but also successfully produced synthetic data that preserve the relationships, dependencies, and statistical correlations between real-world input data variables. This is one of the key contributions of my work. Let me now walk you through the synthetic data generation and machine learning training processes in more detail. As part of my research, I simulated financial transactions for a group of related fictitious banks. First, input variable vectors or feature attributes for POST, NTAC, and TOTUS are extracted from actual fixed income and financing transactions. I then perform data mining by utilizing R-Selenium and RVest functions to automatically web scrape counterparty names, securities issuers, and fixed income instruments from publicly available sources. I then develop code in R that employed various functions for generating random numbers and character strings to populate relevant date, numeric, and categorical variables constituting a typical financial transaction. Crucially, I embedded conditional and Boolean statements in the code, which are designed to capture the statistical features and preserve associations among input variables. I systematically created synthetic data using these rigorous and generative steps for TOTUS, NTAC, and POS, as well as for new unpartitioned test datasets when validating machine learning models. The fidelity tests involve Volcker domain experts evaluating the output from the R code. Only 1 out of the 6 SMEs correctly recognized real data from a printout of a random sample of actual and simulated financial transactions. Moreover, Volcker SMEs deemed to observe variability in synthetic data as a key feature of real financial transactions. However, transactions recorded in bank trading systems are typically less random when compared to synthetic data. The results of the test provide suggestive evidence on the near-perfect fidelity of generated synthetic data. My research adopted trust guardrails to manage the challenge of complexity and explainability of machine learning models. First, I published the code for generating synthetic data, which other researchers can interrogate. Further, future researchers can reuse the code I developed without the restriction of data confidentiality. I also published the code for running the machine learning algorithms to ensure transparency in my experimental setup and calibrating the machine learning techniques. In turn, my work provided a practical solution to the privacy bottlenecks stymieing research in the broader application of machine learning for risk and compliance use cases. In total, my research involved running 36 separate experiments across NTAC, TOTUS, and POS datasets to train and test logistic regression, linear discriminant analysis, and feed-forward neural networks. These models were trained and validated on approximately 16,200 unique synthetic transactions. Logistic regression and neural network models, which are the best performing models, returned perfect precision and F1 scores on POS and NTAC datasets. These two models also returned an impressive 99.72% precision and F1 scores on average for NTAC. The results from both models exhibit stable and robust predictive and classification capabilities, and demonstrate their effectiveness for monitoring, review, and testing. Based on SME Volcker assessment, the results from all three models compare well with actual Volcker monitoring, review, and testing outcomes performed by risk and compliance officers at investment banks. Unlike manual review and testing, which is constrained by sampling size and consequently exposed to sampling risk, all three models can test the full universe of Volcker financial transactions reliably, efficiently, and effectively. Ultimately, the choice between logistic regression and feed-forward neural networks depends on the trade-off between model complexity and interpretability. In summary and to conclude, my research established incontrovertible evidence on the feasibility and effectiveness of applying machine learning algorithms for monitoring, review, and testing. Moreover, my work presented a proof of concept, scalable minimum viable product, and pioneering solution to a prevailing robotics process automation dilemma facing financial institutions when optimizing controls testing processes in the second line of defense. Likewise, my research opened the prospect for the deployment of machine learning algorithms in similar monitoring, review, and testing settings at central banks, other regulatory authorities, and audit firms. By publishing the R code for generating synthetic data which other researchers can redeploy to simulate new datasets for future studies, my work contributes to resolving the privacy bottlenecks stymieing research on machine learning applications for risk and compliance management. Crucially, I lay the groundwork on future research on how financial institutions can best organize their internal control frameworks to keep pace with the rapidly evolving machine learning use cases. Developing metrics for measuring feature distributions, dependencies, and sensitivity statistics by utilizing the R code developed in this research for synthesizing new datasets. Expanding the scope of the financial services machine learning use case deployment atlas introduced in this paper by exploring intersection of my work with similar monitoring, review, and testing performed by regulatory authorities and professional services firms. comparing the performance of machine learning models with actual testing outcomes performed by Volcker SMEs as baseline, and extending the ambit of this research by deploying machine learning models for other Volcker Rule exemptions such as market making, risk mitigating hedging, and liquidity risk management exclusion. Thank you, and that concludes my presentation on machine learning for monitoring, review, and testing.